Hello. When we talk about intermolecular forces, we talk about changing from one phase to another, how a solid becomes a liquid, how the liquid becomes a gas, and all that. So this is what this video is going to be all about. Unfortunately, that means there's going to be a number of definitions. I'll do my best to try to make it interesting, I promise. Okay. So phase transitions are changes in the physical state. Talk about the significance of evaporation. When it rains, you hope the water evaporates in there. Water condenses. Think of the cycle of water. You have water evaporating from the ocean, condenses into the clouds. Then it can freeze and snow in the mountains. When the spring comes, the snow melts down, so the water comes down to the rivers and all of that. So many natural phenomena and technological processes that are very important to our lives are based on phase transitions. Okay? So we're going to be looking at vaporization and condensation, that is the transition between gas and liquid, melting and freezing, transition between solid and liquid, and then sublimation and deposition. That's more unusual because you're going to make transitions between solid and gas and back to solid and skip the liquid altogether. So vaporization means that the liquid is converted into gas. You understand that? Now that takes heat, and we call that the enthalpy of vaporization, and it's always measured in kilojoules per mole. I'm just mentioning this. Obviously, when you're doing problems, these numbers will be given to you, but I want to mention this is a chapter where it's very, very easy to get confused with the units. Okay? Once again, I don't mean that you need to memorize the units. I'm just telling you, watch out when you're doing problems and don't mess up the units. Okay? What happens if you have an open container? I just went and poured a glass of water on the table. Well, it's going to start vaporizing, and keep in mind this takes place at room temperature, okay, until all of the water evaporates. Okay. Now, if you have a closed container, now the vapor is going to start condensing. When the vapor molecules collide with each other, they're going to condense. They go from gas to liquid, so you have an equilibrium. That's what is represented by the Taucher arrow. You have liquid becoming vapor, vapor becoming liquid. When the rates of vaporization and condensation are equal, you get a dynamic equilibrium. Now, you understand equilibrium meaning the amount of liquid and the amount of vapor becomes stable. But it's dynamic. This is very important, and we'll talk a lot about that in college chemistry too, because it's not that vaporization and condensation stop. There's still liquid vaporizing. There's still vapor condensing. But because the rates are the same, the overall numbers don't change, but individual molecules are continuously changing. Okay? And you have an example in there. Bromine can be liquid or can be gas. Vaporization is an endothermic process. Why? Because you have to add heat. Okay? We're moving from the liquid to the gas state, so you add heat to overcome intermolecular forces. That's why sweating helps you cool. It's not sweating, okay? That's something I argue with my biology students, because we talk about how to maintain homeostasis, the internal condition of the body, constant, and say sweating does not cool you off. The evaporation of sweat, that's what cools you off, because it takes heat to evaporate. Sweat is mostly water. It takes heat to evaporate the water. Where does it get the heat from? From your body, because it's on your body. And proof of that is, I live in South Carolina. The summers are extremely humid. Yesterday, it was 98 degrees, and I think it was like 96, 97% humidity. It means when you step out, yes, it's hot. You start sweating. But the sweat does not evaporate because it's so humid. So you know what? The sweat doesn't cool you off, because sweat doesn't cool you off. It's the evaporation of sweat that cools you off. When the humidity is high, that's why they talk about the heat factor. It feels like it's hotter. Why? Because you don't cool. So you're sweating and you're miserable. You're sticky, you're still hot. Now, the reverse would be an exothermic process, so condensation releases heat. I don't know if you've ever noticed that, but right before it rains, the temperature rises teeny little bit because the water vapor is condensing and it releases heat. It's not very significant, but if you have a really good thermometer, you can tell if it's cloudy, is it going to rain or not. You can be observing the temperature. We are talking about a minimum change. Now, yes, when it rains, it cools off because the water is going to evaporate. And when it evaporates, it takes some heat. But immediately before it starts raining, temperature goes up teeny little bit. Now, when you have a closed container, you notice that once the liquid reaches equilibrium, you can see from the beginning it's all liquid, there's no pressure, but now you finally reach at equilibrium in there. So now the volume of the liquid does not change, the amount of vapor does not change, we reach an equilibrium. This vapor in the closed container is putting pressure on the liquid. And we call that vapor pressure, and we're going to be talking about that in the future. But that's the pressure of the vapor that's in equilibrium with the liquid. So vapor pressure is independent on the volume. Obviously, if the container is big, you're going to have more amount of vapor. If the container is smaller, you have less vapor, but the pressure on the liquid is the same for every substance in there. And vapor pressure depends, obviously, on the intermolecular forces. Why? Because if you have a strong intermolecular forces, they don't want vaporization. They're trying to hold the liquid as a liquid. Instead, they favor condensation. They're trying to liquefy everything. So there's very little vapor left, you have low vapor pressure. If you have weak intermolecular forces, then it's easier for the liquid to vaporize. It's less likely for the vapor to condense, so you get more vapor, high vapor pressure. So given these formulas in here, can you explain the vapor pressures, which one is stronger in there? Notice the diethyl ether, it cannot form any hydrogen bonds. All you have is dispersion forces. Ethylene glycol can form 2 hydrogen bonds, and then you have ethanol and water that can form 1 hydrogen bond. All right, but they're very different in size. Okay, so we're going to combine the possibility of forming hydrogen bonds with size. And you can say the ether, remember the one that didn't form any hydrogen bonds, all you have is London dispersion forces. So even though it's big, it has very weak intermolecular forces. Diethyl ether evaporates very easily. It has the highest vapor pressure because it evaporates very easily. If you ever seen ether, I'd use it a lot when I was in college. In Spain, we did a lot of vivisections. And if you didn't keep adding ether, all of a sudden the frog or whatever you was working on would wake up. A very unpleasant situation. Now, when you're looking at molecules that can form hydrogen bonds, ethanol forms hydrogen bondage. So it's going to have stronger intermolecular forces. It evaporates less than ether, so that's going to have a lower vapor pressure. But ethanol can form 1 hydrogen bond. Water and ethylene glycol, can form more. Now, water, in addition to forming hydrogen bonds, is smaller than alcohol. So once again, remember the relationship between intermolecular forces and size. So water is going to form stronger intermolecular forces, so it has a lower vapor pressure. Like I say, ether evaporates without you even realizing. Alcohol evaporates pretty quickly, but water takes forever to evaporate. Ethylene glycol it has 2 hydroxyl groups to form hydrogen bonds. It's going to make lots of hydrogen bonds. So they're going to have the largest intermolecular forces, so it's going to evaporate the slowest, and the vapor pressure is going to be the lowest of all of them. Ethylene glycol, by the way, is antifreeze. And if you accidentally spills some antifreeze, you better clean it because it is not going to evaporate by itself and it's toxic to pets. So don't leave it in the floor of your garage thinking it will evaporate because, oh, well, eventually, if you give it weeks, maybe it will evaporate. I'm not quite sure. But it's not worth the risk. Ether evaporates instantly, alcohol evaporates pretty quickly, well, depends on the temperature and all that, but it will evaporate. Antifreeze won't evaporate. And it's only due to the vapor pressure caused by the intermolecular forces. Now, the vapor pressure increases with increasing temperature. That makes sense. If you look at water at 25 degrees, the vapor pressure is 24 millimeters of mercury. At 50, it's 92. Basically, you have a graph of the kinetic energy necessary. If this is the energy that you need for the water to escape the liquid state, obviously, the high temperature, as the black graph, has a higher number of molecules. Okay? Well, we're talking about evaporating, taking place at room temperature. What's the difference between evaporating and boiling? Well, everybody knows boiling means it's not just the surface of the liquid, but the whole liquid is becoming vapor, okay? So when the vapor pressure of the liquid equals the atmospheric pressure, then you reach the boiling point. That's the temperature at which the liquid boils in here. And standard, we call about normal boiling point, is when the liquid is at 1 atmosphere, okay? One thing that's very important is that during the boiling process, the temperature remains constant, okay? Your boiling water is going to remain at 100 degrees until it finishes boiling. That's one of the reasons you use pressure cooker. You cannot boil water at higher than 100 degrees. But if you put in a pressure cooker is sealed, so now the vapor accumulation here has no way to escape. The vapor pressure increases, so the temperature of the water boiling increases too. So you can reach, I think, 120, 130 degrees for a boiling water. That's why food cooks faster in a pressure cooker. Okay? And obviously, variations in atmospheric pressure will change the boiling point. That's why we talk in the past how high altitude, the atmospheric pressure is lower, the boiling point is lower, so you have to cook food longer. And that's why you have recipes for high altitude. The boiling points of the liquids obviously are going to depend on the intermolecular forces. So low intermolecular forces give you a lower boiling point, because it's very easy. As you increase intermolecular forces, and we discuss these ones, you can see how the boiling temperature increases. This is when atmospheric pressure, normal atmospheric pressure, so ether is going to boil at maybe 35 degrees. Alcohol has higher, boils at 100 degrees, and ethylene glycol, forget it. You're never going to get that hot. Now, this equation, I usually don't tell my students to memorize it. Once again, check with your instructor. But the idea of the Clausius-Clapeyron equation is that it relates two different vapor pressures at two different temperatures. So if you know the vapor pressure at a certain temperature, you can calculate what is the vapor pressure at another temperature. You have the two temperatures, you know one of the vapor pressures, so this is always enthalpy of vaporization given, so you can calculate their vapor pressure. Keep in mind temperatures must be in Kelvin, okay? Why? Because the value of R that will be given to you in here is in joules per mole per Kelvin. That's why you have to have the temperature. And this time, the heat of vaporization must be in joules because R is in joules. So be very, very careful. That's why I told you this chapter, the major problem you're going to have is units. If you write down the units, if you put the heat of vaporization in kilojoules, then you realize kilojoules and joules don't cancel out. That's why it's important to always write down the units as you go. It keeps you from making mistakes. If you don't write them down, you forgot that there are two different units and you go wrong. Be very careful because it's going to happen a lot. Okay. So melting and freezing. Now, you know when you hit a crystal, you increase the average energy of the atom, so it becomes liquid. Okay? We call that melting. The temperature at which you stop heating the solid and it starts melting, that's going to be obviously the melting temperature, is going to remain constant, just like we said when we boil a liquid, the temperature doesn't change. When you're melting something, the temperature remains constant, and once all the solid is melted, then the temperature continues increasing. People ask me, when you came to the States, did you have culture shock? And I used to say no, and then I say, oh, I'm sorry, yes, I did. I remember going to McDonald's, getting a drink, and it was all ice and a little bit of Coke. And I stared at it, and I said, I'm not paying for ice as if it was Coke. 3/4 of the cup or more is ice. And I went to a person who got me the drink, and I said, will you please pour this ice and just fill it with Coke? And the girl said, oh, we put a lot of ice so your drink gets colder. My husband says I argue with everybody, but I can't help it. I'm a chemist, okay? I told her, no, it doesn't matter how much ice. As long as there's a little bit of ice, the temperature remains constant. Now, if you put a lot of ice, it will take longer for the ice to melt, but it doesn't get colder. So we got into a shouting match. The manager came, and the manager told the girl, just pour the drink and give her a drink with no ice. Did you know that most of the machines actually serve you cold sodas? So I got in the habit whenever I go to fast food place or even to a restaurant, I ask for whatever I'm going to drink with no ice, please. Well, the only exception if I ask for tea, because the tea is probably could be at room temperature. But I usually ask. And to this day, it's been almost 50 years, getting close to 50 years I've been in this country. I keep asking for my drinks with no ice, because the drink is cold. The ice doesn't make it colder. No, it doesn't. It keeps it cold longer, but it doesn't make it colder, because the temperature, while the ice is melting, remains constant. So yes, I did have culture shock, and I won. Here you have an example on beaker with ice, and when they first put, this is an electronic thermometer, they put a probe in there, and it's 12 degrees below. But when enough of the ice has time to melt and there's a bit of liquid, it reaches 0 degrees. And it remains at 0 degrees until all of the ice. It doesn't matter how long it takes. How long it takes depends on how much ice you have. But the temperature does not change. You can see it in there as long as there is ice. Now, the moment the last bit of ice is melted, it goes up to room temperature. That's why I say adding extra ice to your drink doesn't make it colder. It makes you pay for ice. That's all it does. Now, if you have a mixture of solid and liquid, like snow melting slowly or something like that, you reach an equilibrium. And if it's cold enough, you're going to have some of the water freezing again and some of the snow melting, so you can reach an equilibrium in here. Okay? Just like we did with the gas and the solid. So the process of melting and the process of freezing take place at equal rates. Once again, there's the same amount of frozen material, the same amount of liquid. Each individual molecule is constantly changing. Now I'm frozen, now I'm liquid, now I'm back frozen. But the overall number remains constant because the rates are constant. It's another example of a dynamic equilibrium. Okay? The temperature at which a solid becomes a liquid is called the melting point when you're looking at the solid. The freezing point, if you're looking at the liquid, is the same temperature. It depends from which point of view. If you're looking at ice, ice is melting, so you call it melting point. If you're looking at water, water is freezing, so you call it freezing point, but in both cases are the same thing. You have two names for the same temperature. Okay? The heat necessary to change one mole of substance from the solid to the liquid state is called the enthalpy of fusion, and it's also in kilojoules per mole. Remember, I told you keep up with your units, this case. How much heat, how much enthalpy of fusion does it take? Well, it depends on the intermolecular forces. So if you have weak attractive forces, you're going to have low melting points, because it doesn't take a whole lot to melt that solid. But if you have strong attractive forces, then you have to add more heat to break those forces, so you're going to end up with higher temperatures. Fusion, and that's another term for melting, is the same thing, going from solid to liquid, is an endothermic process, meaning you have to give it heat. Why does ice melt at room temperature? Because it warms up, right? The reciprocal process, freezing, is going to be exothermic. It releases heat. Let me give you an example. I know this is getting too long, but years ago, we used to go skiing, and sometimes there was no snow in the mountains, and there was snow forecasted for Saturday night, and we all want to know, is it going to snow? I mean, if there was no snow in the mountains, nobody wanted to get up at 6 in the morning on a Sunday to go skiing, right? At the same time, if it didn't snow, you didn't want to sleep. So one thing that at the time amazed me, I was a teenager, and it took me a long time to understand it. Around midnight, my daddy would check the temperature like maybe at 10 and 11. At midnight was the time when he decided. And he'd tell us, yes, it's going to snow tonight. So my mama set up the alarm clock. No, it's not going to snow. She didn't set the alarm clock. He was right 100% of the time, and I was amazed. How does he know? I asked him, and he said, well, if it's going to snow, all of a sudden the temperature should be getting lower as the night advances. But at midnight, all of a sudden the temperature was said to be higher. Why did it get higher? Because freezing is an exothermic process. It was enough that it could be measured with a regular thermometer. It went up 1 or 2 degrees. But it should be going down, and it went up. If the temperature continued decreasing, that means there was no freezing taking place, there was no snow. You could sleep the next morning. Like I said, my daddy did that for years, and it worked every single time. The most unusual change we're going to be looking at sublimation and deposition. Some solids can go directly into gases without a liquid state, and that's called sublimation. Now, deposition is the opposite case, where a solid goes directly into the gas state, again bypassing the liquid state. And you have an example here, iodine. You have solid iodine, you heat it up, it evaporates, there's no liquid at all, and when it touches the walls of the test tube, it deposits again as solid iodine. There's no liquid iodine anywhere. Most common example, dry ice. What is dry ice? It's solid carbon dioxide. At high pressures, carbon dioxide solidifies. Now you get a block of dry ice, you put on the countertop, what happens? Everybody's familiar with the stars producing, looks like steam, right? That's why people like dry ice. You can use it for ice machines, like bands will use it. We use it on Halloween and all of that. But what you have is carbon dioxide solid that becomes carbon dioxide gas. There's no liquid, that's why they call it dry in there. It looks like ice, but there's no liquid in there. So here you have the example, the enthalpy of sublimation, how much heat it takes to go from solid directly to gas, and you have also enthalpy of deposition. That's going to be the opposite, so it's the same number but opposite sign in there. And it's not exactly correct, but you could use Hess's equation and saying, if you look at the enthalpy of fusion, how much heat it takes to go from solid to liquid, and the enthalpy of vaporization, how much energy it takes to go from liquid to gas, you could add them up together and that will give you the enthalpy of sublimation. It's pretty close. You can say that. Okay? This is just what I said now. Sublimation would be the how much heat it takes to go from solid to gases, how much heat it takes to go from solid to liquid, plus from liquid to gas. Like I say, it's a very good approximation. So we're going to be looking at heating and cooling curves. For instance, you have ice, and you're going to heat it up until it boils. We are going to divide this graph, this temperature versus the heat that you're adding, and you're going to see what you're doing in the first section is going to be to heat the ice. Then you melt it in the second, then you heat the water, then you boil the water, then you heat the vapor. So heating the ice, we know this equation from before. The heat necessary is going to be the mass times the specific heat of the solid times the change in temperature. You know this equation now. Okay? Now when we are melting, the heat that we have to add is going to be the number of moles times the enthalpy of fusion, because remember the enthalpy is how much heat it takes to vaporize, also to melt 1 mole. The next stage we're heating water, so we use again the heating equation. Keep in mind, I said water, but it can be anything you want to, but the specific heat of the solid and the specific heat of the liquid is different. So make sure you use the correct number, but it's the mass times the specific heat times the change in temperature. Now we are evaporating, boiling. So the heat of vaporization times the number of moles, and then we are heating gas, so we're using again the same equation, but this time the specific heat is for the gas. All three will be given to you. Just make sure you put the right specific heat for the right part of this line. And let's do an example, because it's much easier. Okay? So you have 135 grams of ice at minus 15 degrees, and you want to heat them to water vapor at 120 degrees. So what I like to tell people is slow down. Let's break it down into phases. We're going to heat the ice, then we're going to melt the ice, then we're going to heat the water. We heat the ice to 0 degrees because that's when it starts melting. Heat the water to 100 degrees, boil it, and then heat the steam to the final temperature. And we calculate the heat for all of them at the end. This is again where you have to be very, very, very careful, because some of these formulas use grams, some use number of moles. And when we talk about specific heat and heat of vaporization, some are going to use joules, some are going to use kilojoules. So be very, very careful with units. If you're not careful with the units, you're going to blow it. If you go slowly, it's really not difficult at all. So when you're heating something, this is the equation. When you are vaporizing, melting, it's a different equation in there. So the heat is the heat for heating up the ice. Now the heat necessary to melt the ice. The heat to heat up the water. The heat to boil the water, and now the heat to heat up the steam. Now keep in mind, and I did plug in the numbers in there, sometimes you use grams because it's mass, sometimes you use moles. Okay, so whenever you use moles, you're going to have to change, you're going to have to be consistent. If you have 18 grams, but you have to multiply the number of moles, you're going to have to change your 18 moles to grams or grams to moles. Just be consistent with the units. This is kilojoules per mole, so you're going to have to change the amount of water. How much did we say was? Oh, they have 135 grams. You have to change it to moles. Okay, so don't forget to change it to moles. Then keep in mind that when you're using specific heats, well, let me just write down the things to watch out for. Grams or moles. If you're heating something, you use grams, but if you're boiling or melting, you need number of moles. So you have to change that. Then make sure you use the right specific heat, because the specific heat for the solid, the liquid, and the gas are different. So look at what are you doing. Are you heating up a solid? Are you heating up a liquid? Are you heating up a gas? Make sure you use the correct specific heat. And then watch out joules or kilojoules, because specific heats, they're usually using there in joules per gram. But enthalpy of vaporization and enthalpy fusion, they're going to be in kilojoules. They're an example, kilojoules per mole. So when you do the calculations, if you go slowly, you realize some numbers are in joules, some numbers are in kilojoules. You cannot add them up together. You're going to have to change it to the same unit. Personally, it will be your choice. I don't care if you give me the answer in joules or in kilojoules. Sometimes, read the problem, sometimes it says, what is the heat necessary in joules? What is the heat in kilojoules? If they're asking you to give particular unit, obviously you have to do that. If they just ask you how much heat, it's your choice. But don't forget that you cannot add joules and kilojoules. You have to transform it. So in this case, I chose to change everything to kilojoules, and my answer is in kilojoules. It seems complicated, but like I said, if you break it down into stages and you solve every stage individually, I know I didn't have room, so that's why I pretty much one long equation. But if you do every stage individually, just like I put in here, I usually write like that, and then I calculate this, and then melt the ice, and I calculate, and I do all of these once, like that. Then I change all of them to one unit, and then just add them up. By writing down as 5 different equations, I think it makes it much easier to do it, less likely to make a mistake. Okay? But these 3 warnings, that's the kind of things I tell the students when you're going to take an exam that this is included. You may want, the moment I give you the exam, to write down someplace on the edge of the exam the 3 warnings, because either one is going to cost you the answer. And because there's 3 different things that you have to watch out for, it's very easy to miss one. Be very, very careful. They're very easy problems. But if you rush, you will make a mistake. When you're heating or cooling a substance, remember that in the phase changes, the temperature remains constant. When ice is melting, it's 0 degrees. When water is boiling, it's 100 degrees. But when you're heating, the temperature changes. Why doesn't the temperature change during a phase change? Because that energy you're adding in the form of heat is being used to break intermolecular forces. That's why the temperature does not increase. Okay? Again, when you're cooling, and energy is being released, we say all of the processes were exothermic. Why is energy being released? Because you're forming intermolecular forces, so that releases energy. But the temperature of the substance does not change. Keep that in mind. Okay? So the physical state of substance can be represented in what we call a phase diagram. A phase diagram shows you pressure versus temperature. You have the solid, you have the gas, you have the liquid, and you have, obviously, when you go from solid to liquid, it's melting. From liquid to solid is freezing. Sublimation goes from solid to gas, deposition gas to solid, vaporization. So you can see all the phases in there. There's 2 points that we're going to discuss in a moment that are very important, the critical point and the triple point. So let's look at the specific example. This is water. Okay? So you have ice, vapor, liquid water in there. Okay, the critical point, and don't worry about the pressure because in kilopascals, but 374 degrees Celsius. if you go any higher than this, you cannot have liquid water. Notice that all of a sudden there's no line, the line disappears. What you end up is a combination of liquid and gases. You have what you have in there has some properties of the liquid, some properties of the gas. We call that a supercritical fluid. But you don't have liquid water as we know it. Going down there, you go to a triple point, you can tell it's named that because you have these three lines that converge in there. At the triple point, you have the solid, the liquid, and the gas coexisting at a very specific temperature and pressure. Okay, so there you have the definition of the triple point. But notice that if you get pressure lower, you cannot have liquid. You cannot, doesn't matter how much you lower the temperature, go back in there, there's no liquid at all. You're going to have gas or you're going to have solid, but you cannot have liquid. Okay? So pretty much it tells you that the curves will indicate you at which temperature and which pressures there's changing from one phase to another. We're going to see what kind of questions they're likely to ask you. So for instance, you have the phase diagram of carbon dioxide. And they ask you, what is the state of carbon dioxide at this temperature and this pressure? So you say, okay, if this is minus 50, minus 30 is probably someplace around here. And 5,000 is going to be someplace around here. So, carbon dioxide is going to be in the liquid state. How about minus 85? Minus 85 is going to be someplace around here. And 100. So this one is liquid. This one is solid. And how about 20 degrees, which is going to be someplace around here, and 100 is going to be gas. So that is a typical question. What is the state of this particular molecule at this temperature and this pressure? And all you have to do is find the temperature and the pressure, see where they come together, and that tells you what it is. The other type of question that I like to ask you is, when you change from this temperature and pressure to that other temperature and pressure, what phase changes are you going to undergo? So in this particular case, they're going to have 2000, let me just say around here. I'm going to try to make it thicker. So you go from minus 100 degrees to 50. Let me see where 50 is located. So it's going to continue like this. Like I'm going to make this a thicker line because that's the second question. Well, what happened? Originally, you have solid, then you get into the liquid, then you get into the gas. Phase changes, solid to liquid, is melting, liquid to gas, vaporization. Again, all you do is go to the graph and see what happens, draw it on it, okay? Very, very easy. So I do have a series of problems, especially looking at hidden cooling curves, practice. Remember, I told you there's 3 different places where you like to make a mistake. The more you practice, the more likely you'll be to get it right the day of the exam. And I have a few examples of studying transitions, what happens in a phase diagram and all of that. So, do you want to try those practice exercises? You know what you have to do. Go to the video description, go to my Washington account, make an appointment, and I will show you the practice exercises. We can even work together and have you ready for the exam.